Okay, thank you. I do feel like saying it, and now for something completely different. Just to give my bio very briefly, I went to university in Manchester to do an electronics degree many years ago. I worked for GPT Telecommunications, defunct company now. I worked for ICL Computers, defunct company now. Yeah, there's a trend somewhere. And then I worked in a technical solution sales and backup, whatever you want to call us, technical solutions for EMC for probably the best part of 23 years now. And now I run my own company, my own consultancy business, where we provide solutions for EMC. So that's me.
Fantastic.
So the idea of this lecture is that I give it to universities most of the time because what we find is that there's many engineers there that come out of university or from college, and they kind of have the theory of EMC drilled into them. There's a bit of information there. Then they get to work for a company like some of your companies, I guess, and they're told, right, go and put the CE mark on the back of this product. Well, how do you do that? So there's kind of a gap in between. So the idea behind the lecture is to sort of say, well, here's the practical bits in between of what you've done at college and what you do when you go out into industry. So what we say is, why do we perform EMC tests? What if we don't? It's quite a serious point. How do companies approach it? What do they do, and what do you need to know? So the first one, why do we perform the tests? Well, there's an EMC directive. If anybody picks up anything electronic these days, even down to vehicles now, you have to have a CE mark on the back of it. So there's part of where the EMC directive comes in. There are other directives as well, but we won't go into those. You put the CE mark on the back of the equipment. It's the law. If you don't do it, put a product onto the marketplace that doesn't have a CE mark on it, or you don't do the testing, you're breaking the law. You will have a better product by doing the testing. That's now become a point that is well built into company directors, because they always like to say, well, we've never had a problem before, so why have we got a problem now? But, so that's one point. And you're increasingly battling an EM environment there, which is much more hostile. Going back to the GPT days I mentioned before, we did some measurements outside where we took an antenna spectrum analyzer, looked at the spectrum between, in those days it would have been, say, 30 megahertz to 1 gigahertz, and we get lots of spikes. We did the same measurement 5 years later, and the whole levels had risen by 20 to 30 dBs. So we can see there, just from a practical test, that things are getting pretty bad out there. So what if you don't? As I mentioned before, you can get... Well, I think you get fined first, but you can go to prison. So, but I think that's if you're a real sort of proper naughty boy. Your product is inferior, it won't work properly. Your product may not work. Loss of revenues. Now, I put that there, telecommunications, no film. What could be worse than no broadband? I mean, when my kids wind me up, I turn the router off. No broadband. That winds them up. So some guy mentioned earlier, you've got 11... broadband devices that are trying to access your router in your house. I worked it out in my house. I think I've got about 13. So it's a good point. How do companies approach EMC? Well, I think without exception, every company I've ever been to has treated EMC in 3 phases. Phase 1, what the hell's EMC? We better go and use a test house. There used to be something like 43 test houses in the UK. Now I think it's more like 30, 32, 33. But then you start using the test house, you're using them every month for a period of time. Your financial director comes along to see you shortly and says, hey, why are we spending £300,000 at this place? What do we get for that? And we've got this. It's a report. That's all we've got. They say, well, can we do something in-house? Second phase, they get some in-house test equipment, start doing some testing in-house. And then third phase is they do a self-declare. They do all the testing themselves. And I mentioned they're using consultants there because there's kind of some test products need to have a notified body or a consultant person checking out that you're doing the testing properly. So there can be a bit there where you can use your own facilities and also do a self-declare as well. And of course, some people don't test. We still get things coming into the UK from China, some of the other sort of low-cost manufacturing areas, and I don't think they do any testing. And every now and again, there'll be a round-robin of testing where they take something around and they find out the things that, hey, these people aren't testing, and hopefully they get taken off the marketplace. That's another subject to talk about, the law side of things and how people police this kind of thing. But I won't go into that now, but you can ask the questions later if you wish. What do you need to know? Now, I mentioned the theory before, where people go to university, attend courses. There are some good books out there now by people like Tim Williams, Chris Marshman. Just look them up on the internet for EMC books. You have to apply the CE mark, so that's what you need to know. The tests involved, you need to have an appreciation of what the tests are that you're going to do, and I'm going to go into that next, where we show some test facilities and what the tests involved. And often the question comes, well, if we pass the tests, we do everything to the standards. Is that it? We've done EMC? Well, no, because the rule is you shan't interfere with other people's equipment, and likewise, that shall not interfere with you. So it could be where you have a piece of equipment out there working in the field, and it still fails because something's interfering with it. And therefore, you're still not passing the EMC requirements. So you have to bear that in mind with your products out in the field. In simple terms, I try to divide it into two sides. I try to divide it into what we call the emissions side and the immunity side. So in emissions, it's kind of what the equipment's giving off, what it's affecting the mains leads by, the communications cables. On the immunity side, we try to do the reciprocal of that, where we actually try to bombard it with energy. We try to put nasty transients, zaps up the back end of the equipment to try and make it fall over. So I treat it in two sides. So on the emissions, we've got conducted emissions and radiated emissions. We've also got harmonics and flicker, where we look at the content of harmonics we put back down the mains. On the immunity, we've got electrostatic discharge. I put some standards in there because I'm aware you're getting the leaflets later, so you can look at the standards at your own leisure if you wish. You've got radiated immunity, you've got electrical fast transients and burst, surge, conducted immunity, and voltage dips and interrupts. Now that's kind of, each product out there usually has a product-specific standard, and that will call up these tests most of the time. But there are some extra ones out there, like magnetic field tests, ring wave tests, telecom surge tests. If you go into the world of military, aerospace, automotive, they have a whole bank of tests that you have to do as well, which is separate in addition to what we're talking about now. So, very simply, this is a picture of a emissions setup where you've got conducted emissions and radiated emissions. So when we do conducted emissions, we're looking the frequency band of 150 kilohertz to 30 megahertz, and we're using this thing up there called a LISN. That stands for Line Impedance Stabilization Network. So you have a mains lead coming in, you have the lead going out to your EUT, and it's looking at the interference that your product is putting on to the mains lines. Then in the other part of the frequency band, we've got 30 megahertz to 1 gigahertz, and this time we're using a broadband antenna there, and we're checking out what's happening inside the equipment. And this kind of area I've drawn there is actually an anechoic chamber, or an environment that you're testing inside. And you're using there something called a spectrum analyzer receiver, which is connected to your LISN, or is connected to your antenna, and that's measuring the emissions. Now, I was talking to some people in the audience earlier, and one thing I missed off there is something called an absorption clamp. And the absorption clamp is kind of a clamp that it kind of fits in between the conducted testing and the radiated testing, because it goes from a 30 megahertz to 300 megahertz. So, again, it's one of those tests that's also there around and about what we're talking about today. Harmonics and flicker, what we're looking at now is what the EUT is actually sticking back down the mains. A lot of equipment now, if it does any switching inside, and most do, so we have a switch mode power supply inside there, it takes the nice sinusoidal waveform and it chops it. When it chops it, if you look at the fast Fourier transform of that waveform, it's putting lots of things back down the mains, and it's affecting what's happening on the mains. So what we do when we're testing, we take a very pure AC source, we take a flicker impedance, which is trying to simulate the impedance of the mains, we take a voltage measurement across the lines for the flicker test, and we take a current meter in line to check out what we're actually putting back down the mains from the EUT, which is busy chopping the mains. Things like inverter drives. Where this test really becomes a problem for many people is that if you imagine a hotel or a big office block, you've got lots of computers, lots of things that chop the mains. You can imagine down the neutral, there's a load of rubbish going back down. Forgot I'm on TV. Lots of rubbish going back down the mains. So it can be quite important for utility companies because it's really affecting their networks. So that's the emissions very simply. On the immunity, the first test I mentioned there was ESD, electrostatic discharge. It's the lowest cost test you'll come across. I mean, often people refer to as EMC as extra money for consultants. It's nothing in EMC is cheap, unfortunately. But then again, it's not like we supply these things thousands a week. It's usually people coming along for equipment. It's very, very rarely. But it is the lowest cost test. It's very easy to do. And it also gives you a guide as to where you might fail in other tests. For example, I don't think I've shown it in this. No, unfortunately, I haven't shown it. The wave shape that we have for an ESD pulse is a very fast rise time and then a bulk of current that comes afterwards. The very fast rise time tends to generate into your equipment. So it can be like a radiated immunity test. So it's a very useful diagnostic test and something that can be used to sort of find possible problems elsewhere. It's easy to do as well for you as the user because setting it up is simple. You buy the equipment. That's a 30 kV unit. Most of the tests we do go up to 15 kV or 8 kV. This is a simple battery-powered tester. So we apply the test directly to any metal parts on the equipment, but we also have to apply the test to a horizontal coupling plane and also to a vertical coupling plane. So it really, the costs come in the ESD generator. The rest of it is just metalwork and resistors to have bleeding the charge away from the ground plane. It's easy to set up. I would suggest anybody that does their own testing, they do buy the standards as well, so you're doing exactly as it is per what the test houses will do. Radiated immunity, this is not the cheapest test to do. This is now where we start talking about we're testing between 80 megahertz and 1 gigahertz. I put in brackets there 2 gigahertz because most people are now having to test at 2 gigahertz. And I've also put future 6 gigahertz there because what we tend to do in the CMC world, I mean, the complaint that comes from the company owner or the person who was having to fork out the money to buy the equipment is, why are we doing this test? Where's the threat? Now, up until 1 gigahertz, there's lots of threats out there. Above 1 gigahertz, it's never been really said, well, where's the threat? But people like yourselves are generating the threat because you're now working up at 2.45 gigahertz. You're working up at 5.7 gigahertz. There's Zigbee, WiMAX. There's all these things happening there which are now causing a problem for people's equipment in homes, in buildings, wherever. So that's the frequency range. I've also said it's probably the most expensive test setup because we need an anechoic chamber. These things are metal rooms. You have to line the metal room with some absorbing material to try and simulate outside. They're very expensive. You need RF amplifiers because we're now talking about a band that goes from 80 megahertz to 1 gig, 1 gig to 2 gigs, 2 gigs to 6 gigs. So effectively, you need to have two, possibly three amplifiers. Directional couplers, where we're trying to monitor the forward power for calibration purposes. An RF field probe, that's paramount to this system because we're trying to work out what field we're generating inside our anechoic chamber so that we're not over-testing or under-testing. You need a signal generator and power meter. So Colville's company, for example, Agilent, they provide that kind of equipment that drives into our amplifiers, which in turn drives the antennas and gives us field. And it's becoming more and more important that you have software control because the amount of time and effort you'll put into this testing, if you don't automate it, will be days, weeks, months, possibly. So as a very simple test setup, you can see there that we've got the anechoic chamber, and inside the chamber where we're generating the field, we've got the antennas and the field probe. Outside the antenna, we've got a kind of we've automated the system, so we have an automation system, but we're driving into the amplifiers, into directional couplers, then switching the outputs to go into the antennas. So this is trying to automate it for people like our test house customers, where time is money. So the quicker you can do the testing, the more revenues they make, and you have to pay them. And then I also mentioned their signal generator and power meter, power heads, and some sort of automation software. We do use some optical capabilities in this, where we actually link from the field probe inside to go back to an optical measurement there. So we have an electro-optical conversion inside the chamber to look at the field strength, which in this sort of testing I'm talking about, we're talking about 10 volts per meter field. But if you're an automotive customer, you're talking about possibly 200 volts per meter. If you're working in the aerospace and military areas, you could be talking about 3,500 volts per meter, but a pulse test. But we're talking about serious levels there, because of course you don't want your fighter aircraft to drop out of the sky. So these tests will go in things like these. So I mentioned before about this is what you'll see in most test houses if you go there for standard EMC testing. You can't see the metal work, of course, because we've got it lined with these what we call radio frequency absorbing materials, RAM, sometimes it's referred to. This is basically foam material, which has an impregnation of carbon inside it. And what we're doing is when we're generating field, we want the field to go directly at the equipment we're testing. We don't want it reflecting off the sidewalls. So this material absorbs the energy to stop reflections. this is the material down there in one block form. And you can see there's lots of blocks all stuck to the walls in there. What you see there, in your world of the sort of trying to supply set-top boxes into houses, these set-top boxes are also having antennas inside. So you're trying to flood the house with energy so that people can use their smart devices, their computers and so on. So what you also need to know about these anechoic chambers, you can use them in the other way, which is to look at antenna measurements. And that picture there shows an antenna measurement chamber where that's actually a satellite going into space. So we're looking at how that works in space before it goes up on a payload and is launched around the planet. I also mentioned about a test where we go up to 3,500 volts per metre, or in the extreme, 7,200 volts per metre. And that's using something called Category L for DO-160 testing aerospace. And what we do there, this is like a big microwave oven, where you see that thing at the top there, it's actually a paddle. And the paddle rotates. And down the bottom there, you've got some antennas, and the antenna generates a field. The paddle rotates at a certain speed, and it floods the area with energy, and your equipment and the test is inside there being bombarded by this energy. So that's a nice test setup. These are relatively low cost. This is EMC on extreme. This thing here is 105 metres long from there to the end. They put aircraft inside their vehicles. It's based in France, in a place called Granat, somewhere down south. Yeah, very nice down there. And we have a very high power generator with a dish there, and these two devices move in and out. These are bafflers, and then we have absorber material all around there, so we can focus the beam right at the very end of the chamber. And there's just one more extreme picture where we're testing a helicopter inside this one. And there we actually use this for electromagnetic pulse testing, also for aircraft and helicopters. So there's radiated immunity. The next thing we'll talk about now is looking at sort of transient type tests. And so we've spoken about an ESD pulse where you walk along. We've all picked up our car keys, tried to get in the car. Ooh, got a zap. Or you walked across a nice dry carpet, nylon carpet, and zapped something. We talked about radiated immunity where we're bombarding the equipment with a field that we're generating. These tests now are looking at what we put on the mains leads or the communication leads. And what you can have now are these kind of generators. I think my battery's going. These kind of generators where we can build lots of tests inside one box solution. So it makes it much more cost effective. Just to give you an example of the idea of cost effectiveness. In the old days of, say, 15, 20 years ago, you'd have had to have had 3 separate generators to go inside that box. That would have cost you about £60,000. Now this box on its own costs about £15,000. So it's still expensive, but we've made some moves there to make it more cost-effective for the engineers. And these are the kind of test levels we can do inside. These are way above what the test levels require. But as I said before, EMC doesn't stop just with the standards. You've got to think about over-testing to make sure that you've got a much more robust equipment. So the first test that unit can do there is something called electrical fast transient testing. Why do we do that? Well, there's a very simplistic way sort of network there. And really we're trying to simulate what's happening on an opening switch. So if you look down there, at the very start of the opening switch, it's very fast rise time at very low amplitude. But as the switch opens, it's much larger transients but high amplitude. So lower frequency but higher amplitude. So it looks a bit like that on a scope. How do we simulate that? It's difficult to do. And a lot of these test standards that have come out from EMC have started back in 1980, 1990. So when we first started doing this test, that's what the actual test pulse was decided to be. So each test pulse that you saw in the scope picture has now been decided it will be 5 nanoseconds rise time, 50 nanoseconds duration. What we do a burst of them in 50 milliseconds if we're testing at 5 kilohertz with a duration of 300 milliseconds between them. And if you go to higher frequencies like 100 kilohertz, because what works at 5 kilohertz? Not many things. But 100 to 140 kilohertz is a more realistic transient level to test to. So this is also in the standard now for 100 kilohertz. This is a typical test setup. So again, it's very easy to do. You get hold of the standard, you set it up in a lab, you have a ground plane, you've got your generator there with a coupling network. Because when we're doing these tests, we want to test the equipment. We don't want to test the rest of the network. So you have to have a decoupling network as well as a coupling network. There's your equipment under test. It's insulated from a ground plane. So we apply the test on the mains leads, and away we go. Just do the test. It's very easy to do. But if you've got any I/O cables or cables that are longer than 3 meters that are non-power cables, we have to use something called a capacitive coupling clamp, which is that thing there. It looks like a large metal Toblerone. You put cables inside it, flatten it on top of the cables, and apply the test there. So again, a very easy test to do. The second test the box can do is surge testing. So where before that was looking at simulating an open or closing switch on a circuit, we now have surge, which is looking at indirect lightning strikes, a surge on your waveform that comes. So set-top boxes or anything inside your house computers, for example, should have protection inside them for secondary lightning or secondary voltage surges. So this is now testing them. What we have to do with this test is we have something there called an open circuit voltage. So we send this open circuit voltage inside a piece of equipment, and hopefully you've got some protection device, a metal oxide varistor, for example, flashes over there, and therefore it doesn't go anywhere near your equipment. Or if it gets inside the equipment, you want to make sure there's nowhere for it to flash over or cause any problems. So if it does flash over, you've got to make sure that you have an instantaneous flow of short-circuit current. So often this is referred to as a combination or hybrid wave. And these are the kind of couplings you have to do. So this is for single-phase and three-phase, and we have to apply the test with a 2-ohm source impedance for differential mode, 12-ohm source impedance for common mode. We have to do shielded cables. We have to do symmetrical communication lines. I'm quickly flicking over that because the point I'm trying to get across is that by the time you're finished, you're testing at 0, 90 degrees, 180 degrees, 270 degrees, 5 positive, 5 negative. We have to do differential mode and common mode testing. We are allowed to provide 1 minute between test pulses because the way that these protection devices work inside your equipment, they work by heat. So they heat up as they absorb the energy, and if you don't allow them to cool down, they stop working. So that's why you're allowed to have 1 minute in between. Now, test houses love this test because, as I've put there, it can take 8 hours of testing for just one particular test. Right? So 8 hours of testing, I think it's £1,000 a day now for test houses. So all of a sudden, when you're doing all this testing, it suddenly makes it, maybe we should have our own equipment because test time is mounting up. And you should have other things on the facility, for example, current limiting, because the problem with this test is that, as we showed before, if we send this open voltage circuit in and we just keep sending it into the equipment and it flashes over, it's going to blow your equipment to smithereens. This test has got energy inside it, so you can damage the equipment as well as personnel as well, so you have to be careful with it. So a current limiter capability is very useful because it stops the test as soon as it sees an overcurrent test, and you don't blow up your equipment. You can fault find what the problem is, and straight away you can have a solution for it. The third test that the box does is something called voltage dips and interrupts, and that's as simple as it sounds. However, you do have to be able to provide a 500 amp inrush current, and you also need to be able to switch between two different voltage supplies in between 1 and 5 microseconds. That's quite difficult to do. So, again, like an engineer once said to me, well, why can't I just turn it off and on at the switch at the wall? Well, you can, but it's not the same thing because you're not doing the same sort of test. It doesn't meet the standard. So we're trying to do a voltage dip there. We're doing a voltage interruption there. And they call it a motor start. It's sort of things you see on vehicles when they're trying to do what's called it's when you start your engine on your car anyway. That's not really a test that you'd have to do. But they do have something called a voltage variation test where you have to ramp down over a certain time, then ramp back up. And that's applicable to some countries, but not to the UK. So you don't need to do that test here. And there's a typical test setup where you have a motorised variac. So you've got the 100% live coming in, so that's sort of like up to 230 volts. And then you have a motorised variac inside that can go down to your 40%, 70% or 80% test level, or with the motorised variac, whatever level you want to. But the standards refer to 40, 70, 80. So this device here switches, so it switches between the two. And the EUT, if it's susceptible to interrupts in the mains, and if you've got switch mode power supplies inside your EUT, it will be susceptible to it. It's a good test to make sure it stands up to brownouts and problems in the field. So that's all those tests inside that one box I showed you earlier. The final test, which I'll talk about, which is one that's very common, is what's called conductive immunity testing. So we've spoken about the radiated immunity test, where we're blasting the equipment with radiated fields between 80 megahertz and 1 gigahertz. That cable, that EUT over there, though, has cables. So the cable acts as an antenna, which takes interference in. So now we test down from, and I've not written the frequency on, but it's from 150 kilohertz to 80 megahertz in brackets 230 megahertz, because some tests refer to 230 megahertz as well. So we take a signal generator, an amplifier, and we have to get it onto a cable somehow. Software control again, power meter there to look at the test level we're going to generate. This is the calibration setup. So this CDN stands for coupling decoupling network. So what we do is we short out the input and the output. We check we get a level of 10 volts RMS or 3 volts RMS, depending which standard you're working to. We test it that way, and then we take the calibration parts away, and we do the testing, just repeating the RF onto that CDN and do the testing. Now, if it's a mains line or a power line, you have to use a CDN. But you imagine if you've got an EUT, and I've seen some in some labs where there's 15, 20 cables coming off a piece of equipment. If you had to have 15, 20 CDNs per product, these CDNs are quite expensive, so you could be spending 15 to 20,000 pounds on some CDNs. So then you're given the alternative as you're using something like an injection clamp. And an injection clamp is basically just a row of ferrites. You unclamp it, put the cable through, clamp it down. So you'd use that for all the other types of cables other than mains or power lines. So you can save some money that way in your test setup. There's just a picture there showing a typical CDN. So you've got the CDN there with a shorting adapter. You have to put it into a certain network. So we're trying to duplicate a 50-ohm network. So you do the calibration, take all that away afterwards, and just bring the RF straight into the CDN. But when you do the test, you then bring the mains in and the mains out to the EUT when you're doing the test. Is it a pass or a fail? How do you know? I mean, I've said that it doesn't stop with the standards because you might go out into the field and find out there's a problem. So what the standards are trying to do is give you guidance as to whether you have passed or failed, or at least to something that be quantified. So if you look at the emissions thing, we have limits, and often you refer to people referring to something like EN 55022, Class A, Class B limits. You hear people referring to generic standards, where they're light industrial, heavy industrial. They're all giving limits there that you need to be aware of if you're doing emission measurements, because if you've got levels really low, then what's your problem? But if you've got levels really high, obviously you need to know if you're going to break any rules. Immunity. What they do in immunity, they give you a failure criteria. And the failure criteria, that's trying to give you a guidance as to, it helps you determine whether the performance is okay when you've actually applied these immunity tests. So, for example, at one extreme, you could have no failures allowed at all. So if you were in an aircraft and something happened on the aircraft, we did some testing once on a 747, and we were trying to, I don't know if you remember 15 years ago, there was a big deal about whether you could use mobile phones on aircraft. So BA gave us a 747, and Virgin gave us a 737. And we were taking on RF amplification and a system with a correct kind of signal generator that could do a simulation of a mobile phone. So we went around the aircraft, the back, the front, into first class. I've never been there ever again. It's very nice. And we generated RF there. And then in fact, it was me on one occasion and a colleague at the time, we went into the avionics bay, and we went on the flight deck. You can't call it a cockpit. We got told off for saying that terminology. And we measured on there to see what the fields were. And, how do you determine what happens there? Now, there was a sign on the 747 where lots of dials, and there's a sign there saying, during HF transmission, dials will go to the right. So all these dials must go like that when you do a transmission, and then come back again. So it's a whole case of where we're trying to say, well, is that a pass or a fail? And that's what I'm trying to get at anyway. So you've got one extreme where you don't want to bring the aircraft down. The other thing might be you can a reset's acceptable as long as there's no damage. So there's all these failure criteria. So if anybody's supplying equipment into, say, Virgin Media, I guess they put onto the supplier, you're allowed to sort of go to a certain level, and if you go beyond that level, then you're a failure. If you're below that level, then you're a pass. We'll look at functionality to make sure that they're working, because I said before, it might pass the standards, but it's still got to pass in the field. Does it work in the field? I haven't gone into this bit too much because I've learned quite a lot today, so thank you for inviting me. It's been very educational. So I just put down a few things there which I thought, these things are quite interesting, because with me working for GPT, we used to refer a lot to the ETSI standards and go off there to see the people there. So if you are interested in the standards that they apply, take a look at this website there. I think Colville was talking about power measurements today, and he mentioned the IEEE standard there. I know sometimes we get asked about that for using our power meters for doing that kind of testing as well. So sometimes there is a mix over there as to what happens in what we try to do. What do people in your industry do? I mean, that's it, really, at the top there. My experience of going to see people that work in the set-top box, the communication industry, is test. They're always testing. Great. Because, you've got to check. I mean, what happens if you get a piece of equipment shipped in from Korea or from America or from the UK, and they say it's got the CE mark on it, it's got the right certificates, but does it actually work when you actually put it into a setup? Often people used to refer to this saying, well, this thing's got CE marking, this has got CE marking. You put the two together, everything's fine. No, it's not. You've got to test it as a system so that when it goes into the house or into the system, into the work, you stick a printer onto a computer. Does it still work? You've got to make sure it works. You'll often hear this word due diligence, when people say, well, what am I supposed to do? Well, due diligence, a company of my size, we're a very small company. If I was trying to do some EMC testing, should I have the same facilities as what someone like BAE Systems or Virgin Media or anybody has? Well, you've got to show due diligence for the size of company that you are, that you've applied the right amount of tests. And if you have a very safety-conscious piece of equipment, you've got to do more tests. Check good communication in the home. I know my limited experience of talking to the likes of Costas and talking to other companies that supply services into the home. Does it work in the home? I know one company, they actually have a house in the middle of nowhere that's set up. It's got sofas in there, it's got TVs and all the rest of it, and they take a set-top box in there and see if it works in the environment that it actually goes into. And then they take antenna measurements around the place to see if it's actually getting around the building. And the other thing, I've recently been contracted to be involved in a European, it's very early days, so I can't really say too much about it, but they're going to look at things like cyberspace, cybersecurity, how things work in environments. And if you look at modern building materials, when we're in the process of building a shielded room, but using things like Celcon and Kingspan materials. If anybody's had an extension done or a new house build, they use this material now, which is an aluminium sheet with a thick insulation aluminium sheet. Well, that's what our shielded rooms are made like, except there's much more complication there. But you're effectively building a shielded room inside your house. Does it work inside the house? So you're looking at interaction there. So that's sort of things I see when I go around, and things that I've noticed that probably are affecting things that you do. Now, I just want to put this on there at the end because it's thanks to Costas that I've been able to put some things together today and been invited today. So we put a facility in there for Costas where it's used for EMC and antenna measurement applications. We set off with this initial plan where this long piece there is the actual test chamber. This is a control room. And what we're trying to do in facilities like this, we know this is the business end where we're generating field or looking at fields coming off equipment, but we also have to have a load of equipment where we're going to be monitoring or exercising the equipment we're testing. So we need to have an isolation there as well. So you've got a metal wall in between, but this wasn't good enough because it had a door in between, so that wasn't really working out. So in the end, what we did is we put the chamber there, and we put a shielded control room on the side there, and in between, on that wall, there's quite a lot of penetration panels to get cables in and out. And then you'll see there that we've got sort of, I don't know whether you can see, but there's like a gap that is the outer wall and the inner wall. And that's because this is using something called a hybrid solution, where we use something called ferrite tiles with a foam absorber on top of the ferrite tiles. The reason why we use ferrite tiles is, you remember the previous few things back where we were showing the material, which is the foam material, looking like a comb shape. If you want to go to very low frequencies using that kind of material, you've got to have something like an 8-foot, 9-foot long piece of foam material because of the way it works. Well, straight away, this building is going to have to be the size of like a 10-metre size chamber to be able to use that kind of material. And about 15, 20 years ago, they invented the ferrite tile material. And ferrite tiles are basically little tiles. They look just like what you have in your bathroom, except they're made out of a ferrite material. And you completely line all walls and the ceiling with this kind of material. It has an effect from 30 megahertz to 1 gigahertz. And then to make the chamber function from 1 gigahertz to 18 gigahertz, we use the foam material there, which is a special match material. You also can see in there that we've got a turntable, because when we're taking emissions measurements or we're generating field at a piece of equipment, we don't just do it to one face. We want to see what's happening when the thing's moving around. So we rotate it around all the different angles, trying to find the worst level, and most likely it'll be from the front or from the back, where the cables are coming out. So we need to be able to rotate it. So that's got a turntable inside as well. And we also have some material on the floor, because when we do the radiated immunity test, where we're blasting the energy at the equipment, you take the energy straight at the equipment, but if you have a metal floor, it'll bounce off the floor. So we try to sort of quell that or absorb it, so we have a direct line of field attacking the equipment. And that's what it looks like. So you can see there that we've got a metal floor, ground plane, we've got the antenna there, we've got the absorber all over the ceiling. Behind the absorber are these ferrite tiles I mentioned. There's a turntable there which you can't see, and this is the antenna which is being used to probably either make, I think it's being used for immunity on this occasion. And this is another antenna, but looking now from the Virgin Media sign the other way, you can see there that that's what we call a bilog antenna. And that has a biconical antenna element at the back, which will work from 30 megahertz to 200 megahertz, and a log periodic antenna at the front, which will work from 200 megahertz to 1 gigahertz, and probably a little bit higher. You'll also see that this material we've used at the back there is a little bit different looking to this material. That's because this is the business end for doing the EMC measurements. This is the business end for doing antenna measurements. And we're trying to sort of put an environment there where we don't want too many reflections coming off the walls, and we're trying to see what the equipment does when it's trying to communicate with lots of other ancillary equipments or mobile phones, smart machines, or whatever Costas uses it for. I'm sure you can ask him much more questions about what this thing does and what it does with it. And that's the end of my talk. I made it really quick because I know we were running out of time.